Kinematics of elastic collisions. When considering collisions, we generally talk about two different reference frames. First, fixed center of mass. In other words, we have two particles, 1 and 2, coming at each other with the same but opposite momentum. This is before the collision. On the other hand, in fixed target reference frame, the second particle has zero momentum, and the first particle has a non-zero momentum. After the collision, in the fixed center of mass reference frame, we'll have momentum p prime, or one particle, scattered at angle theta, and minus p prime of the other particle. In the fixed target reference frame, we'll have momentum of the first particle and some other momentum of the second particle, p1 prime and p2 prime. As you can see, the kinematics is simpler in the center of mass frame. Therefore, we'll use center of mass frame everywhere for solving kinematic problems unless specified otherwise. What do we mean by elastic collisions? We mean that there is no change in particle state except for momentum. In other words, in elastic collisions, initial kinetic energy is equal to total energy of the system and is equal to final kinetic energy. For the fixed center of mass reference frame, we'll simply have p squared divided by 2m plus p squared divided by 2m of the second mass equal to p prime squared divided by 2m1 plus p prime squared divided by 2m2. Or, which we can rewrite as p squared divided by twice the reduced mass equal to p prime squared divided by twice the reduced mass, from which we get that absolute value of momentum before and after collision are the same. Question: what about the speeds of the particles? Since m1 v1 will be equal to m1 v1 prime after the collision, we get that the velocity before and after the collision, or rather the speeds before and after the collisions, will be the same. That's another nice feature of the center of mass reference frame, that speeds don't change after the collision. Finally, let's write the Lagrangian of the system. Well, we already wrote Lagrangian for particles moving in radial potential. What's missing is motion of the center of mass, which we can write to be half of the total mass m times r dot squared, capital R, which is the center of mass velocity squared. Capital M here is simply m1 plus m2. Thus, we can find generalized momentum, which will be given by partial derivative of Lagrangian with respect to velocity, and it will be equal to P, defined as mu reduced mass times r dot, where r is the relative position of the two masses. Note that this P is not a conserved quantity, though the magnitude of the momentum is constant at infinity. In other words, before and after the collision, the magnitude of P stays the same. In center of mass frame, we have the velocity big R dot equal to 0. Thus, we can write R1 velocity in terms of the relative position velocity R dot. And then we can rewrite momentum P1 as m R1 dot, which gives us m1 m2 divided by capital M times R dot, or mu R dot, which is the definition of the generalized momentum P. Thus we get that P1 is equal to minus P2 and is given by the generalized momentum P, defined as reduced mass times relative position R dot.